And let me start by thanking the 22 parallel session speakers from Atlas and CMS who summarized about 54 papers that came out in 2014 alone, out of which 12 were presented for the first time here at iChap. These searches search for a vast range of theoretical ideas, and they cover a vast number of results that I'm supposed to be covering here, even just counting the ATV results. So I'm completely ignoring anything that came out on 7TV and only focusing in ATV, and even then, this is impossible to cover all. So what I've done here is instead I'm trying to attempt to cover the diversity rather than the completeness. I'm trying to give you a little bit of a flavor of everything that is being searched for rather than giving you the complete picture of any particular area. At the same time, what I've done is I have put all the hyperlinks of all the actual papers that came out in 2014 into my slides in the topics where appropriate. And whenever I am covering a result from one of the two experiments inside the body of the talk, I tried to put the corresponding result from the other experiment into the backup slides. So my backup slides are about as long as the talk, or a little longer actually. So the outline of my talk is I'm giving you an introduction, then I will talk on resonances, dark matter, and then unusual signatures, including long-lived particles. Among dark matter, I have split this up into 3 pieces: antisocial, semi-social, and social. According to whether the dark matter comes alone, comes in pairs, or comes in a huge family. And in the resonances, I am splitting it up into singly produced resonances and pair-produced resonances. But before I get there, I wanted to talk a little bit about the standard model backgrounds and give you a sense of what are the features of the standard model backgrounds that we key in on in the vast majority of these searches. And the first feature I wanted to remind you of is that the one lepton on plus met cross-section is about 10 to the 6th times smaller than the all-hadronic cross-section at pp collisions of ATV. The next feature that's worth remembering is that the Higgs cross-section is about 10 to the 10 times smaller than the all-hadronic. And finally, the dilepton same sign plus met signature is about 10 to the 12 times smaller than the all-hadronic. Just looking at these scales gives you, I hope will convince you that leptons, met, Z, H boson are all excellent probes in search for BSM physics, and that's exactly what is being used. And the one other big picture feature is that if you look at these plots here, you see that the jet cross-section dives exponentially as a function of jet PT. And similarly, the number of jets, cross-section dive exponentially for each of the various standard model particles, meaning W plus jets, Z plus jets, and top plus jets. The more jets you add, the more the cross-section goes down, and it goes down exponentially. So what this means is we exploit both of these features for the standard model by defining these 3 variables, which is the most commonly used variables in these searches, and you'll see this in lots of places as you read the literature. There's 2 other characteristics that I wanted to point out. First is endpoints. Kinematic endpoints play a crucial role in many of the searches. There are 2 types of endpoints. There are endpoints that are designed by their very nature to control mismeasurements in the detector. An example for this is alpha T. And then there are endpoints that nature gave us that are just germane to the physics that we look at. And that's the transverse mass, for example, in either leptonic W decays or in 1 lepton decays off top. And finally, the last structural element, if you wish, of these searches is jet substructure. As we push to higher and higher mass particles that we're searching for, when they decay into jets, or when they decay into bosons for that matter, the final products of the dijet systems that you get out of a W, Z, or Higgs decay are boosted more and more. And that means that the jet cones start overlapping. And you can sort of make this very simple argument that I've made here and argue that somewhere around 200 GeV in momentum is when an overlap of jets start happening for the kind of cones we used at ATV. De facto, these jet structure algorithms really come into play and dominate the results at about a TeV maybe, or 800 GeV or so. So a typical search strategy, therefore, defines a low spectron signal region using all of the ingredients, or some of the ingredients that I've talked about on the previous slides. You then extrapolate an expected background yield from carefully designed background control regions, and measure the accuracy of your extrapolation in independent control regions in data and simulation. And as everything in life, success typically comes from a combination of brains and brawn, meaning strategy and execution. And so let me move on to the actual results. I'm starting with resonances. The simplest resonance that I could think of is dilepton on searching for peaks in the dilepton mass spectrum. And what you see here is the E plus, E minus spectrum and the mu plus, mu minus spectrum, both from Atlas. And there are two types of searches that are being done here. Either you search for a resonant peak at some high mass, or you search for a shoulder from a contact interaction. And what you can see in these distributions, first and foremost, is that the highest mass dilepton event found are about 2 TeV. And then the limits interpreting these spectra in terms of limits on new physics, Z primes are ruled out up to about 3 TeV, and contact interactions are ruled out up to about, in extreme case, of 26 TeV. You can then do the same thing and just do bump hunts in any old combination of particles that you can think of. And so what I've tried to do here is give you a little bit of a feel for how this translates into what is the highest mass event that I could find out of any of the plots that either Atlas or CMS are showing. Rather than showing you the individual plots, I'm showing you a table, because there are too many of them. And I'm doing this for fermion pairs and for boson pairs, for final states with bosons. And you can sort of see that the highest mass events range from about a TeV for tau-tau to about 5 TeV for dijets. And similarly, when bosons are involved, they range from about a TeV to about 4 TeV, depending on what kind of final state you're looking at. And correspondingly, the highest mass limits that are being placed range in the range of 1 to 5 TeV scale masses across a very wide range of final states for singly produced resonances. And the star here is for analysis that use jet substruction. You can see there's a few of these. You can also search for pairs of produced resonances. And in resonance pair, I've made the same kind of table, and you can see from this table that we're probing here somewhere between 0.5 and a TeV scale physics across, again, a very wide range of final states. And the totality, the experiments then put out these bar plots where the x-axis gives you the scale of mass that is being probed, and then you get a reference to where and what is being probed. And what I've talked about is singly produced resonance and pair-produced resonances. Now, switching gear a little bit, when you have particles that are being produced that actually decay into our favorite bosons, W, Z, or Higgs, you find that it is often favorable not to just look for bumps, but just to look for spectra or for excesses in final states. That then becomes tricky because for a given new physics model, often you have, depending on parameter space, multiple types of final states as expressed in the number of bosons and the types of bosons that you're looking for in the final state. Once you do that, immediately it becomes obvious that given that we know the branching fractions of what this stuff decays into in the standard model, the final state it looks very, very different. It may look almost entirely like an all-hadronic final state, or be completely dominated by leptons, as in the 4W. The best search strategy is therefore generally to take a given model and combine all the signatures that this model would provide and make a attempt a branching fraction independent sensitivity as much as possible. And so I'm showing you here an example from Atlas. Here, what is being done here is we're searching for vector-like T-prime pairs, pair production, where the T-prime can either be decayed to Higgs plus top, Z plus top, or W plus B, and then we depict this as a branching fraction for T prime to WB on the x-axis and Higgs top on the y-axis, and whatever is left over is then Z top. And as you see here, if one uses only an analysis with a single signature, ZLL plus B, then you're really restricted to sensitivity only when the 2Z plus top final state is almost 100%. However, if you combine many different final states, then you can achieve almost uniform sensitivity across the entire plane of possible branching fractions. And so a search strategy for final states with multiple W's, Z's, and H's ideally combine multiple final state signatures, and you'll see this a couple of times more in my talk as a theme. Let's switch on to dark matter. I said that I would be talking about dark matter in terms of antisocial, which means proton-proton and nothing, semisocial, which largely means that there's at least one state close by to the dark matter particle and heavily compressed, or very social, which means you have a whole family of new particles to search for with large cascades as endpoints. As you can see, this has the largest number of papers out because it has the largest variety of signatures on some level. So hunting antisocial dark matter, you either look for an ISR gluon, W or Z, or you look for vector Boson fusion production. In the mono X searches, you find that all of these have been executed. You generally find that the backgrounds are differ quite a bit in these different analyses, as well as the level of background differs dramatically. In the mono W search, it is furthermore, one needs to remember that there's two diagrams which the same initial state and the same final state, and therefore the amplitudes interfere, and depending on what the coupling is of the new physics to UU bar or DD bar, this interference is either destructive or constructive, and you get about almost 3 orders of magnitude difference in expected yields depending on this ratio of couplings. If you then put these on some comparative plane where typically what's chosen is an effective field theory application to compare with the nuclear and cross-section, you can see that in general the monojet analysis has the largest sensitivity. However, when you have a sign flip in the coupling, then suddenly the W recoil becomes the most sensitive. Looking at VBF, I look at this, the Higgs search that you've already heard about, Higgs to invisible via VBF, as a proof of principle for VBF to nothing in general. And so let me just point out that this kind of selection gets you down to a standard model background where one would actually be able to see 100% Higgs to invisible, as you can see in these plots. But what is more interesting for standard model searches is that if you then compare the VBF versus the Z recoil, you find that the mass ridge for Higgs to invisible with VBF far exceeds the corresponding ZLL and BB. Moving on to semisocial dark matter. What if the dark matter is not completely alone and there is some kind of mass split? And what you'll find is that the dark matter, as discussed in the mono X searches, is not sensitive. It will be missed by experiment if this delta M is not negligible. We therefore need to have search strategy that cover all possible delta M. And just to give you a visual impression of this, I've taken the stop to charm LSP search from Atlas. And what you see here, this is the monojet search. And this here is a charm tag search. And you can see that as delta M increases, you're going away from the complete degeneracy between stop and the dark matter particle. The sensitivity decreases, and you recover this loss of sensitivity by requiring explicitly the charm tags, and the combination of both covers the entire space. bottom line, the take-home message is that while mono-X searches are very powerful for antisocial dark matter, we need dedicated search strategies targeting compressed spectra in order to cover all possible scenarios of delta M in the new physics spectra. There was a fair amount of talk on discussion in the parallel session about stop gaps, meaning gaps that the LFSG is leaving behind. So let me point this out briefly with a couple slides. So what you find here is that there are kinematic regions here for which there's no MET because the dark matter is produced at rest in the stop rest frame. And if you go below the resonance, you get a large distribution of the dark matter PTs in the rest frame, but exactly at resonance, you don't. So how do we deal with this? At large dark matter, these gaps will eventually get closed at large values simply by luminosity and ISR boost. And for very small dark matter masses, you need precision top measurements, like, for example, this here, which has just started to encroach on the relevant area. Then switching to social dark matter, this is a vast range because it has a vast number of signatures, because you can make up any old spectrum you like. And what we use is we use supersymmetry as a framework to define the cross-section of the things we're looking for. We then distinguish colored new physics from weakly produced new physics. We're then selecting anywhere between 2 and 10 jets with or without leptons, photons, B tags, jet substructure, MET, lifetime, the list goes on and on and on. So there's a huge program that is being executed here in order to search for colored new particles. Similarly, we are searching for weakly produced new physics. And here we're focusing predominantly on leptons as signature, but there's also analysis with 0 leptons, photons with and without B tags, jets, WZs, Higgses, lifetime, the whole range. And the PT threshold of objects that are being used in these analyses go as low as 5 GeV for leptons and 30 GeV for jets. It's way too many results to talk about this in a talk where I have only 30 minutes to present all of the entirety. And therefore, I've picked 3 results to flash them here at least. I'm picking a combination between 0 and 1 lepton, an exploration of branching fractions between 4B and 4 top, and using the Higgs in order to go after electric production. So the first, CMS combined a 0 lepton and 1 lepton analysis in order to push out the stop mass reach at the limit by another 75 GeV. Second, in principle, if such things as gluinos exist, they could decay down to your dark matter particle via either 2 Bs, 2 tops, or a top and a B, or some combination thereof in different branching fractions. And CMS presented an analysis at ICHEP where they show how the sensitivity decreases as the Q value in the K shrinks because of the mass of the top. And electric weak production, we have a very large program of final state that are being searched for. The interpretation is within a gauge-mediated supersymmetry baking scenario where you have the neutralino either go via a Higgs or via a Z into a gravitino and in the final state. And then you, in order to map out the entire range of masses versus branching fraction, you need a number of different final states. And what's shown here is which range of in the parameter space is dominated in sensitivity by which of the final states. You then combine all of these final states and you exclude the range below this black line. In addition, there are searches for a large variety of unusual signatures, and I don't have time to even read off the slide because I'm told I'm already out of time. But what you see is that it is a large diversity. Let me just pick on one specific one. I'm picking on the displaced dileptons, E's and mu's. What I find interesting about this particular search is all it requires is that you have 2 displaced leptons. It does not require that they come from a common vertex. It it does require opposite flavor. It works, therefore, on an assumption that you're pair-producing something, but maybe not pair-producing something, and then that these pair-produced things both fly some distance, decay at different vertices, and all you require for the interpretation is that you start out with a hadronic production in order to get a large cross-section, and then you make yourself different ranges of D0 to find your signal regions, and as you can see, for small separation, you get still significant backgrounds, and as you go larger, there's simply no backgrounds left whatsoever, and then you express the limit as a function of the mass of a hypothetical colored particle and the lifetime. And too small a lifetime, and you don't have enough efficiency to place a tight limit. Too large a lifetime, and you don't have enough efficiency because there's an upper lifetime cut as well. Summary and conclusion, well, we looked all over the place. No new physics was found anywhere we looked, and we're going to do it all over again when we get the new collisions in 2015. Thank you very much.
Thank you very much, Frank. So we have time for one urgent question, even if it is not so urgent. Yes.
How general are your searches in SUSY? I mean, are you using a very general platform for the? I mean, given that the more naive expectations have not been seen, have you generalized the framework of the search to?
So we started out with very inclusive searches that were only very faintly motivated by the details of supersymmetry. We then specialized those searches into a variety of scenarios that are hard to dig out beyond the standard model physics, from the standard model physics, but still trying to be as generic for the signature as possible. And as we haven't found anything, if I may say so, the specialization into more specific SU scenario has increased in order to be able to express then limits in scenarios of gauge mediation or M-Sugra or whatever your favorite natural supersymmetry, your favorite scenario is. So there's short answer, all of the above.
Okay, thank you very much again, Frank. And our next speaker is Marcela Carena.